Yeah, I think what Peter just mentioned is also a case of personal data, basically. So since 2 years or so, 3 years, we have in the EU a law called GDPR, General Data Protection Regulation. This law should protect the privacy of personal data, basically, all kinds of personal data. So a name, a birth date is, for example, a personal datum. So GDPR imposes restrictions on storing, sharing, and processing of personal data. The problem with the kinds of data that scientists or neuroscientists especially are working is that they cannot be easily anonymized or pseudonymized. They are very high dimensional. So for example, such an MRI data set contains millions of voxels, and maybe even time series of voxels, of voxel activity. This is a lot of information, basically. And it was shown already that very few of this information is sufficient in order to reconstruct the identity of the person, the data subject from which this data was recorded. And this would be a problem. So if the privacy of persons that participate in scientific studies is breached, this could lead to a number of potential harms. I don't know, for example, if health status information of this person somehow is openly visible in the internet also, for example. And currently, there are many large-scale initiatives like UK Biobank, Human Connectome Project, and so on, that are collecting thousands of features from millions of people. And of course, also health records in general, digitalized, and therefore, there is a lot of potential, basically, for sensitive data to get into wrong hands. So these are just examples for two studies that show that it's very easy to reconstruct the identity of someone when you have a good machine learning classifier, for example. So in this example on the left from network neuroscience, you just needed like 40 edges from a functional connectivity matrix to reconstruct the identity of a person. And the study on the right, it was just 15 demographic attributes like name and so on. And not name, of course, it's a bit too easy, but like attributes you wouldn't expect that could easily identify you. And of course, these attributes are important for biomedical research. These are exactly the things we are looking for, right? So exactly these things that characterize a person is what we are looking for in order to individually find therapies for this person, basically. So we cannot really circumvent this problem, basically. We can only reduce risks. So in the following, I try to describe potential solutions, basically, to run brain network model simulations in a cloud environment and also to process neuroimaging data in a non-secure environment. So cloud environments are inherently non-secure. The internet is non-secure. It's an open network. And cloud environments typically are shared resources. So you share these resources with many other tenants, and there is possibility for that data leaks between such different tenants. So a complete elimination of any security risk is not possible. So we try to find a good balance between effort to keep the data secure and the remaining risk for the individual. Just a short overview of what kinds of data we especially are working with. So we have to construct brain network models. We have tail-1-weighted MRI, we have diffusion-weighted MRI, T2-weighted MRI often. We often also record EEG or MEG and fMRI. And these data we then translate or aggregate or we generate models out of these data, basically, that are based on structural connectomes. This is a description of the connection strengths and time delays of interaction between brain regions. We often use aggregated region-wise fMRI time series to compute functional connectomes or to look at the large-scale brain dynamics. And we use also surfaces from reconstructed from the T1 MRI, like the cortical surface or the skull surfaces. It's even possible. So I saw a publication where there was a classifier that was able to reconstruct the face from a dephased MRI. So things like this are possible. Don't ask me how, but it seems it's somehow possible. So we need to take these risks, which are could be very subtle, but they exist basically. As an outline of this talk, I would just mention some general classes of security risks in cloud platforms, then some ideas how to counteract these risks. Then I will talk about how such a user agreement could look like and the roles in our cloud computing environment. So the goal is basically to enable researchers to use EBRAINS cloud services with personal data in a manner that is compliant with GDPR, basically. It should, of course, use all of the state-of-the-art available data security measures that are existent. So this is a fast-moving field, data security. So the people who are working in data security are currently often concerned, for example, in a post-quantum world, they call it, when quantum computers are there and they already think far ahead, because a lot of security concepts would break down when there would be quantum computers, for example. So this is a very interesting community. Article 32 of GDPR. So this is basically as concrete as it gets from the side of GDPR. So this is basically what they tell us what we should do in order to protect data. So when this law was conceptualized, I guess the people who thought about this law didn't really think about that there are such high-dimensional data sets. So there are no concrete recommendations for these kinds of data. The law seems to be more written for usual data that like name, address, and stuff. So we have to find some creative ways to basically integrate all these different requirements. So GDPR says we should take into account the state of the art and should implement appropriate technical and organizational measures to ensure a level of security appropriate to the risk, and should use pseudonymization and encryption of personal data. We should ensure ongoing confidentiality, integrity, availability, and resilience of processing systems and services. We should be able to restore the availability and access of personal data in a timely manner in the event of incidents. And there should be schedules for regular testing of these security mechanisms. So this is a bit vague. So basically, they tell us, find out how to protect your data best. So this is what I will present next. So a general class of risks is, so these are 4 very generic classes of security risks that exist in computing infrastructures in general, basically. So there's logical leakage. Basically, in computing, you send data all the time from one computer to another computer, and these channels are more or less open. So everyone could basically access such a channel. So the internet is composed of many computers. Basically, the information is routed worldwide over many computers, and all of these computers basically can look into these data packets that are sent around if they're not encrypted. Wireless networks are very unsafe. So there are many basic routes or possibilities to exploit networks like the internet, which is our primary network. Another risk is a break-in on a live device. basically the device is currently actively processing personal data, and somehow an attacker gets able to look into this working device and to leak out some data. So there are, for example, viruses that can do this. They are in the background and look what is going on and read out or dump the memory and send it, open up connections to some other computer and send it there, for example. So there are often news in the media about backdoors that were found in some prominent software and so on. Then also the software that is running the cloud computing infrastructure, it may easily contain bugs or backdoors that lead to such an isolation failure, where basically the data of one tenant cannot be isolated from the data of another tenant. And of course, there could also be malicious insiders. So if you have someone in your team who actively programs backdoors in your code, so this would be very hard to circumvent. So this security concept really tries to look at all the different angles that can occur. Of course, you can always remove security measures. It's always about a reduction of risks. There's never a full security. Full user impersonation would mean that an attacker gets access to secret information that allows to impersonate the user. For example, the user lost their passwords, or an access token was captured while in transit, for example, a cryptographic key was leaked, and so on. And hardware leakage is when basically a hardware piece gets into the wrong hands. For example, a hard drive that contains sensitive data. So if such a huge data center gets decommissioned, often, for example, the hard drives need to be degaussed, and there are several things that need to be taken into consideration to avoid hardware leakage. Of course, we cannot guarantee the security of hardware where we don't even know where it is, in some data center somewhere. So the security concept basically tries to be independent of this problem. So we try to find solutions on the side of software that would also solve the hardware leakage problem. So here are some ideas, or basically the ways such generic risks could be addressed. So the first risk, logical leakage, the typical countermeasure against data getting lost is authenticated encryption. What this is, we'll come to in a minute, basically. So encryption is basically making the data unreadable, unintelligible. So it's the data was made into a code that cannot be simply interpreted. So this is like the most important security measure, I would say, that exists. Usually the basic fundamental security measure is encryption. And we also need some form of authentication to ensure that the data was not tampered with. Break-in on live device. Also here we have authenticated encryption as a standard countermeasure. And so data must not be present in unencrypted form during the attack. So data shouldn't be stored unencrypted, written on a file system somewhere. So for example, if suddenly there's a power outage, the data would be there on the hard drive, unencrypted. Or if someone is able to just dump the file system, bypassing OS level security mechanisms, for example, this is possible, it's very well possible. They would have the entire file system, basically. So data can only be considered secure if one can guarantee that the data was not open for the entire duration of the attack, that there are no unencrypted files existent in the file system or in the memory that then would have been probably dumped into some hibernation file or so. So also cryptographic keys, of course, themselves are then sensitive data and must be protected. So cryptographic keys, which are used to encrypt data, must themselves be encrypted, and the decryption of these keys again requires a special infrastructure, which we'll come to in a minute. To counteract full user impersonation, when an attacker gets access to like a password or so, again, here we can reduce risks if we keep such secrets, if such secrets are relevant for as few personal data as possible, basically. So if we have the fewest keys possible, or we split up the data or data sets into as many different keys as possible, basically, this would basically reduce the risk of this risk. Hardware leakage, countermeasures for this is, as always, authenticated encryption of data and keys, and then secure deletion. I'll also come to in a second what this means. And no unencrypted cryptographic data encrypting key should be on the same device as encrypted data. So the keys that encrypt data encrypting keys should be separated from the keys that encrypt the data, because otherwise, if the attacker gets both keys, then all the security is gone again. And swap files, memory dumps, and so on, these should be securely deleted or also encrypted if present. And therefore, in order to counteract such very subtle risks in such some cases, GDPR basically says that data protection should by design and by default be implemented into the software architecture. So when you begin to think about a software architecture at the very first moment, basically a cloud computing architecture, you should already start to think about how you can implement this architecture in a way that is inherently by design or by default secured in some way. So the data controller should implement appropriate technical and organizational measures for ensuring that by default, only personal data which are necessary for a specific purpose of the processing are processed. And this obligation applies to the amount of personal data collected, the extent of the processing, the period of storage, and the accessibility. We should in particular ensure that data is not made accessible without the individual's intervention to other people. So the data should by default be protected. And this is, of course, this is a discrepancy with the nature of computing systems, basically. So as I already mentioned, we would need, or we would have available a number of security measures to protect. So let me just briefly run over these measures again, so that we get a feeling for them. So we have only software measures, as I mentioned, because we cannot really guarantee the security of the cloud infrastructure themselves, so the hardware side, the hardware backend. So authenticated end-to-end encryption simultaneously assures the confidentiality and authenticity of a data set using digital signatures and codes that confirm that the message came from the stated sender and was not tampered with. So this is really the central pillar of data security, and this method basically simultaneously ensures that a file that I just obtained is the exact file that the sender sent away. So we would notice if someone manipulated this file in order to, for example, deceive us, to get secrets from us, for example. So sometimes a file gets caught while in transit, then it's tampered, and then it gets forwarded to the recipient. The recipient would not know that it was tampered with, but it somehow contained some information, or it was tampered with in a way that would allow for either reconstructing the data or reconstructing the secret that would allow decrypting the data. So we need both authentication and end-to-end encryption. So I guess it would be quite good if all stored files, all files that are written in a file system, so-called data at rest, that contain personal data, must be encrypted at all times. So this would basically ensure that there is never personal data existent on a physical long-term data storage device. Except, of course, for the data controller who initiated this processing, but this is their local computer then in this case. Public key cryptography would be a nice way to exchange data between a user and some remote cloud computing location. Because in public key cryptography, you simultaneously generate a public and a private key, and the public key is only used to encrypt the data. It can be publicly known, while the private key can be used to decrypt the data, and this one can be kept a secret. So we can easily share public keys over the internet. We don't need to worry that they get into the wrong hands. All that they can be used with is basically to make the data unreadable. So this is nice. This takes off these worries that the data encryption leaks on the way from the cloud infrastructure to the user's computer. So before we upload, and this is what is meant by end-to-end encryption, before we upload the data to the EBRAINS cloud, we must already ensure that it is encrypted, because this is the moment where basically the user or the data processor or data owner entrusts us with the data, basically. And from this moment on, we are responsible for the data, or EBRAINS is responsible for the data. And at this moment, it's so-called data processing on behalf. So a data owner or data processor is the legal owner or the legal processor of a data under GDPR. And with this concept, EBRAINS would basically never become a data owner. We would only be data processors on behalf, which is a concept that was allowed by GDPR, which is possible under GDPR. Basically, we want to circumvent all the problems that come with owning personal data by never being owners, but only processors. So key architecture is basically an architecture that ensures the proper storage of cryptographic keys or other secrets, basically. So if data is always encrypt authenticated, if data is always encrypted, then basically the only risk for data breach falls back on the key. So if the data is unreadable, then the only chance to leak this information is if the key is leaked, because then the data can be made readable again. So a proper key architecture would basically ensure that the amount of data encrypted with one key is as small as practically possible. Of course, the keys that encrypt this data should never be stored in encrypted form, because if they are stored unencrypted and close to the data themselves, then all the hacker needs to do is take the key and decrypt the data. So we need a two-level key architecture. We have at a low level, we have keys that encrypt or decrypt data. And at the higher level, we have keys that encrypt or decrypt lower level keys. And these two levels of keys should be separated. They should not be present on the same device. Because otherwise, again, the hacker could simply use the high level keys to encrypt the lower level keys and then the data. So instead of, so they should not be present on the same device. This, however, brings the challenge that if they are not present on the same device, we somehow need to bring them from the one device to the other device so that we can decrypt the data encrypting key. And there are also mechanisms to transmit such high-level keys via non-secure channels. And a keyword for this is salted hash challenge response authentication mechanism, where we basically have dynamic secrets that are exchanged and processes that ensure the authenticity of the communication partners, and also where we don't really store secrets in a fully readable manner, but in a slightly manipulated manner that wouldn't allow reconstruction. Yeah. And such key architectures, for example, are already implemented in OpenStack, which is a platform, a container orchestration platform that we are using anyway in this cloud. Access control, basically, like the name implies, ensures that only the people who are allowed to can access something. So we control the access to something, and this is usually done with passwords in combination with tokens that contain also cryptographic keys to prevent such unauthorized access, and also to provide, this is more important here, secure delegated access for connecting different cloud services. So basically here we have a system that would be independent of any manual user interaction. The user would basically select the data on their local computer and give us the parameters basically for the processing. But from then on, it should be only machines and no human that would ever come near or close to this personal data again. And this is what is meant by secure delegated access. We need to ensure that these machines can talk to each other and know they are legitimate. So at this point also, hackers could, of course, invent such client machines and could at some point interfere with this communication and leak out data. So basically, so-called authorization flows or authentication flows convey authorization decisions or access decisions. So a system decided that a user or something is legitimate, and this decision must then be propagated basically. And for this, we have tokens. So tokens are used. So this is, you know, this when you have like when you go on a website and you want to order something there, but you don't have a login there, and suddenly they say log in with your Google account or Facebook account or something. In this moment, you authorized something, and this authorization decision is then propagated via cryptographic tokens between these different companies here, even in this case, Google and I don't know, wherever what you ordered there. This is a generic way basically to convey the legitimacy of the authorization decisions over insecure networks basically. And such authorization flows, basically we have a so-called a management system basically that tracks the user identities and provides such access tokens to authorize the application's ongoing access to resources on the behalf of the user without the need that the user needs to really do something. And these code flows usually, to make this secure, they usually provide a double check. So a user would enter some credentials. This is how the user verifies itself, and then the application verifies itself by showing its legitimacy by returning a secret code. And this basically, this two-way authentication basically is a bit more secure. Problematically, in this case, we trust the application that it is able to keep such secrets. But the problem is we cannot really trust our applications that they can keep such secrets. So applications in a scientific context are usually open source. or they can be easily decompiled, or because we have browser-based cloud infrastructures, such secrets would also end up ultimately in some browser variable, or the tokens which are sent around, they can be also captured and read out, or there can be backdoors programmed into such programs. And also programs internally do not encrypt secrets, so they may also be read out simply from main memory. So there are a host of problems again with such authorization code flows. And there is another mechanism, PKCE, proof key of code exchange, which generates dynamic ad hoc secrets that would again circumvent this problem. Yeah, of course, passwords must be sufficiently complex and also stored in a robust keyed and hashed and salted form. So these are basically transformations of passwords that do not allow an easy reconstruction of the actual passwords, while still allowing whether the password is correct or not. Yeah, and typical things you would implement like session timeouts, forbidding of shared accounts. So one account should be exactly mappable to one natural person, and this person should be the data controller of the or must be the data controller of the personal data. In this case, there's never a change of data ownership, basically. Yeah, and of course, these accounts, there should be no direct access, basically, to accounts that that run services, basically, because otherwise these accounts or these services could be tampered with. And APIs, so the interface that a user is provided with, should be as minimalistic as possible. So the user should really only be able to do the minimal set of things that would be needed in order to reach the goal of the processing. Okay, firewalls is a standard measure where we basically block the ports of a computer. So computers interact via channels called ports, and firewalls seal these ports. So this is a nice thing in order to lock out external attempts to somehow access our accounts or our computers. And yeah, therefore we would configure these firewalls explicitly such that only pre-registered and approved network connections would be allowed to come through. Yeah, so because we cannot really guarantee the security of our applications, and applications typically use many third-party libraries, the security of which again cannot be guaranteed. So, and also you cannot guarantee the security of the OS you're running with or of the cloud infrastructure. So we would somehow shut ourselves off of the remaining world by pulling up firewalls and also sandboxes. So sandboxes are a bit like the internal equivalent of a firewall. So sandbox is really what the name implies. Is basically the application lives in a playground where it cannot do too much damage. So a sandbox where you put your kit is a soft place where nothing bad can happen, basically, and it's shielded from the outside, more or less. So this is a sandbox. We isolate the available namespaces of the process from the full set of namespaces, and therefore isolate this process from the remaining stack of this computer. And we would then, of course, configure such sandboxes in a way that they cannot write data outside of the sandbox. So basically, in the moment that a processing job starts and data is being decrypted, at this moment we pull up walls that guarantee that data cannot leak out. Okay. And as the last step of every application's lifecycle, we send the results the encrypted results back to the user. These walls are still active. Maybe we dig a small hole in the walls to send the data back. And before we tear down these walls, we securely delete everything, every personal data and keys and so on that were inside the sandbox. There are mechanisms that automatically dump the contents of memory, of main memory, onto long-term storage devices. So we also need to ensure that this is not the case. Yeah. Okay. Then there are additional standard measures you will often find in to secure cloud platforms like host firewalls, antivirus software, Trojan detection, anti-spam, application layer gateways, DDoS mitigation, encrypted communication, host-based intrusion detection, and so on. We would harden the operating systems and also the virtual machines and so on, such that they only provide the smallest area for attack. So we actively uninstall all the programs that are could be a risk, basically, and install only programs we trust, basically. Then an additional measure would be that we use separate and dedicated accounts, and also the privileges of these accounts should basically be reduced to the absolute minimum rights in order to function correctly. And ideally, of course, credentials, if they are unknown to human users, basically you can say there's no way that a human user ever could have logged into this account, basically. And this, of course, is also a database and storages. So sometimes you spend a lot of effort to protect your software, and then you forget that you also have a database or some external storage that is not protected. So these should also be protected. Yeah, and we can also, of course, make sure that accession to our accounts is only by pre-registered and appointed network addresses, from which we know and which we collected prior to the processing, from which we know that they are secure or that they are legitimate. There's a lot of software out there for monitoring and incident handling. So there's software that basically detects when there are intrusions or anomalies, basically. So this software would basically monitor the network traffic that goes in or out of a system, and features of the system, and such intrusion system would basically then correlate events and look for unusual correlations between events, basically, and to become active, basically. And in case of an intrusion, it would, of course, be very secure if, as soon as the system learns that something unusual is going on, to be on the safe side, to immediately securely destroy and delete everything. So this is would be a safeguard, basically. Yeah, unsuccessful login attempts are, of course, a red flag. Yeah, so these kinds of software should be installed and should be running in order to detect such events. And also, this is also described under GDPR, such monitoring software must write out logs, basically. So everything that happens with the system, and much more importantly, everything that happens with the personal data must be logged and written into a backup log. So if the data was accessed, if it was transferred, all of this, all data accessions and transformations and transfers must be explicitly documented with timestamps, the user who did this, and so on. These log files must be, this is the only thing that really must be backed up, basically, and ideally also be ensured that it can endure for a longer time. And in case of such an incident, GDPR requires that reactive and corrective measures ensure a forensic analysis, what happened, what went wrong, and basically at this time there should already be an incident response plan that ensures timely, effective, and orderly response. And if such an incident happens, competent authorities and data subjects must be notified. And also the European Union Agency for Network and Information Security. Secure deletion and data ephemerality refers to basically that so secure deletion is when you hit delete on your computer, then the file is usually not really removed from the long-term storage of this computer, but just the index table where your computer holds your whole set of files. In this index table, just the flag is cleared, but the file is actually still there and could be easily recovered. And this recovery is possible even if, if this is a hard drive, a magnetic disk, this recovery is even possible if the data was overwritten 7 times, for example. So there are studies that was possible 20 years ago already. So there's still a signature of this data in the magnetization of the hard drive. So even if you would overwrite the sector where the data was, it could still be recovered. And to counteract this, there is overwriting software, which overwrites the sectors, which complicated patterns that make it more easier to restore, and overwrites it many times. And degaussing of decommissioned magnetic media, we have no influence on this, basically. We just hope that it is done. Yeah, and data ephemerality is basically data should be as ephemeral, as fleety as possible. So ideally, it should never be stored in an unsecure location. There shouldn't be backups in unsecure location. Of course, in secure locations, this is even mandated by GDPR. There should be backups of the data, but not in a cloud environment. And immediately after processing, or if processing fails or was aborted, so there must be a mechanism that ensures that data is securely deleted even if there is a power outage, or if the program just hangs up, for example. There must be basically a daemon that runs in the background, or the parent process of the processing job, basically, or a process that is very close to the root process, basically, must ensure that even if child processes suddenly die, that someone does the cleanup, basically. And if you have such a nice concept now in place and implemented, of course, you need to make sure that it's always up to date. So if a new security standard is released, it usually doesn't take long until someone breaks it again. Such a concept is always only as good as the software that you use to implement it. And therefore, a regular schedule for review and testing of security mechanisms should be put in place. Cloud users, or especially data owners and data processors, must be informed transparently over the security concept. They must understand it, and they must basically, in the user agreement, they must basically confirm with their signature that this security is sufficient to protect the privacy of their data subjects, basically. Of course, this is all documented, and regular backups are performed of the infrastructure. And critical security updates released by the OS, or like virus signatures and so on. All of these things must be regularly updated. Yeah. And human resources is also a factor. So employees must be ideally trained, so they must be adequately informed about these security mechanisms that pertain to their work. This could be workshops or campaigns and so on. And one could also provide such information at salient locations in the cloud infrastructure. There could be pop-ups, for example, if a user is about to do something they shouldn't, they could warn of danger. But this is already, so ideally, in my opinion, the whole software is designed in a way that it's impossible to do something something that could cause a leakage of data, or something that is illegal under GDPR, basically. Yeah, so this implies or includes also that source codes must be reviewed and the review documented and stored. And the application, so on eBRAINS, the idea is that users program applications and make these available on the eBRAINS cloud to other users. So before this happens, before a user makes a software public that is used for personal data processing, it should be tested under live conditions while monitoring network traffic and discrete write operations. We would like to exactly know what does the software do, how does it, which ports does it open, which processes does it interact or communicate, and so on. So we want to know the flow of data in order to detect something suspicious. And if such an infrastructure is then in place, we share basically the responsibility for our compliance with GDPR. The data owner shares this responsibility with us, the data processor, and basically this would be this is a possibility for a legal data processing in the cloud environment in the EU. Yeah, this is called processing on behalf. And yeah, so this concept basically should allow processing on behalf. But yeah, as I mentioned, this is not clearly defined in GDPR. So these are suggestions basically how one could achieve that. Basically, what this involves also is that a contract for data processing on behalf is formed between eBRAINS and the data owner or data processor. And the service provider, eBRAINS, must then adhere or comply to the instructions of this controller. They must implement adequate technical measures. There must be some kind of confidentiality agreement in place with employees that come somehow close to confidential information. Of course, we cannot simply pass the data on to another sub-processor without authorization of the controller. And we, or eBRAINS, must make available all information to the controller to demonstrate compliance with GDPR. Basically, this is all written up in such a usage agreement. And the data controller must basically agree to this agreement in order to be able to use these cloud services. Before that, the user cannot use the cloud services, and so there could be, for example, tokens handed out in exchange for a user agreement. So there's a user agreement, the two parties agree on a certain processing. The processing is clarified, it is written down. In exchange for that, the user gets a token that allows them to use a supercomputing architecture with the software and their personal data. Despite all of this, there are still risks. It's never possible to really fully secure this whole environment. Yeah. This is the risk we have to live with. And with this concept, we would basically waive the responsibility that this cloud user is the legal data controller, or is everything doing in a lawful way. So the data controller gives us his signature, all of this is guaranteed. And it's not our business to ensure that, basically. So with this, the status of the data controller or data owner remains unaltered by using the cloud. There are security measures that basically shall ensure that neither cloud administrators or any other person is able to access this data, and therefore, even if the data is somewhere else, the ownership doesn't change, because the system is designed such that the data controller is the only person that can access it or delete it. So the owner or controller does not cede their legal responsibilities for data protection. And basically, in such a processing on behalf agreement, we would, however, give the data controller everything they could possibly need in order to ensure that everything is legal under GDPR. So if they think this is not the case, they can give us instructions. And then we either follow these instructions or we say we don't do your processing. Yeah, so we are not permitted to access, modify, copy, or use the data. It's a black box. Data is automatically uploaded, processing starts, is being done, result is given back to the user. We haven't been in between. Yeah, and this is all explicitly clarified. It's also known to the user that this data is stored on servers located in the EU, and that all of this and all the encryption mechanisms and so on, that all of this may again collide with some national or international laws that pertain to the research of this data. So there are, for example, countries where it is illegal to encrypt data. So this, yeah, would then be a problem for this user. So this is just a short overview over the user agreement. There are many more pages. Just how it looks like. Basically, it's like a contract that you have between EBRAINS and the data owner. And therein we have all what I just said. And yeah, this is then captured with a signature. So highlights of this agreement is basically the user is the data controller or processor, and EBRAINS is the data processor, but again, never the owner or controller. We get instructed, and yeah, basically I said all of this. So this is the concept of data processing on behalf. This logging, the user must also be aware that we write some meta information about this processing. So this is our responsibility, and therefore the user must be aware that like the processing of the data, what happens to the data, and so on, that this is logged and this written somewhere. Of course, there will be no personal data in these log files, but information about personal data and what happened to this personal data. So GDPR doesn't explicitly mention logs. However, if you get sued by a data subject, then these logs would basically help you to demonstrate that you complied with GDPR and that you followed all your legal obligation and tracked suspicious activities. So we log data access, data modifications. So one important GDPR principle is integrity. The data must be correct. And these logs basically prove that modifications happened for a reason. Data subjects have the right to look into their data. And yeah, so basically with these logs, we can also proof that this is fulfilled. Yeah, and it can also be used to ensure that the user used to process the processing the cloud services in a legal way, basically by looking at which IP addresses or user logins used this services. And basically, consent is the condition we are invoking here to ensure a lawful processing. So basically, the legal method with which we are allowing this to happen is consent. The data controller, data owner consents to this. Sorry, the data subject has given consent that this processing of his or her personal data is in the purposes of this processing, basically. So this consent must be there. This is the legal basis for this data processing on behalf. Without a consent of the data subject, there's no data processing on behalf. So we end up basically with a cloud computing environment that has just two roles: administrators and data controllers of personal data. There's no one else. People that are not data controller of personal data cannot use this cloud service, or they can only use it with data that is not personal, basically, or that doesn't fall under GDPR. The cloud TVB and EBRAINS cloud services are designed, implemented, and deployed such that it is impossible for human users to access the data once they have been sent from the data controller to the cloud. Yeah, so it's in a fully automatic way and actively prevents access to human users. And basically what administrators do is they ensure that these cloud services are fully functional and perform technical administration of the service applications, like installing, updating cloud services and performing regular maintenance. They monitor also the cloud services and the security monitoring, and are the first ones to get informed when something unusual happens, and they would basically restart crashed servers, clients, daemons, software, basic cloud software, basically. So the administrator basically needs to somehow access a service account on the involved front and backend system in order to perform these actions. And the data controller is a person that is allowed to make use of a certain data set to transform it. Basically, this is a user from the EBRAINS community, and the actions of a data controller involve selecting such a cloud service, using the data transfer clients of EBRAINS to perform a secure end-to-end encrypted transfer, and then the cloud services. So from these actions, the following needs for the permissions ensue: none. So the data controller basically needs no permissions at all on a computing system, because it all runs in a fully automatic way. The user basically would just click locally on a button, and from there on, everything happens automatically. So a workflow basically could look like the data controller signs such a data processing on behalf user agreement with EBRAINS. The exact processing and all involved parameters, are exactly specified in user agreement. And only in exchange for a user agreement, the user obtains a usage token that they can use to authorize an upload, followed by processing in EBRAINS. So the user clicks on a link upload at the EBRAINS website. Then EBRAINS asks for this token that the user got for the user agreement. Then a file selection window opens. The user selects the personal data files they want to use in the processing or in the simulation. and the user clicks OK, and basically from then on the uploader encrypts and compresses the files. The public private key pair was created in a secure process at the computing side, and only the public key was sent to the user's browser. The uploader sends the files directly to the secure process at the computing side. Then the data processing happens, and then the user gets informed by email when the results are ready for download. And for downloading these results, there was a public-private key pair generated this time on the user's computer. So we only had to send the sensitive public key from the user's computer to the processing side, where it gets encrypted, and it can then only be decrypted again on the user's computer with the corresponding private key. Yeah, this would basically ensure this the secure transmission of the data. And if we then see that the data was if we verified that the data was correctly downloaded, everything gets securely deleted, what happened on the processing side and also the keys. Yeah, and this is would basically be a workflow. If something happens in between, the whole process would basically be aborted, everything deleted and started from scratch.